So to find zeros of a polynomial, we also call that finding the x-intercepts of our polynomial. But what we're going to want to do is we're going to want to set, our polynomial equal to 0. So in order to find the x-intercept of a linear function, we're going to let y equals 0 or f of x equals 0, and then we solve for x. So let's go ahead and find the 0 for f of x equals negative 1/3 x plus 6. So I'm going to go ahead and let 0 equal negative 1/3 x plus 6. And I need to solve for x. So I'm going to subtract 6 from both sides. That gives me negative 6 equals negative 1/3 x. Now I can either divide by negative 1/3 or multiply by the reciprocal. So I'm going to do that. That gives me positive 18 equals x. So my x-intercept is when x is 18, y is 0. Now, linear equations can either have one x-intercept or no x-intercepts. That's in the case of horizontal lines. Because horizontal lines are parallel to the x-axis, they're never going to cross them, so they're never going to have an x-intercept. When it comes to finding the zeros for degree 2 equations or quadratic equations, we need to use the quadratic formula. This quadratic formula right here, okay? It's important to remember that parabolas either have 0, 1, or 2 x-intercepts. What does that even mean? Let me draw a picture. So there's our beautiful xy coordinate plane. Let's pick a better accent color like green. If my parabola has 0 x-intercepts, that means it probably starts above, for instance, the x-axis, and it's never going to cross the x-axis. If it has exactly 1 0, that means that its vertex is going to be on the x-axis. And if it has 2 x-intercepts, that means its vertex probably starts below the x-axis. So it would have 2. You can also do this by looking at the discriminant. That's what we call b squared minus 4ac. So let's go ahead and find the zeros of x squared minus 3x plus 2. The thing I like to do to start is to label all of my coefficients. So I have a equals 1, b equals negative 3, that's a negative 3, guys, and c equals 2. And I'm going to go ahead and plug that in and solve for x. So I have x equals negative b, which is negative 3, plus or minus the square root of b squared minus 4 times a times c, which is 2, all over 2a. So let's go ahead and simplify this. So I have x equals 2 negatives make up positive. 2 times a is 2 times 1, which is 2. That gives me the square root of 9 minus 4 times 1 times 2, which is 8. So now I have 3 plus or minus the square root of 1 divided by 2. Well, the square root of 1 is going to be 1. So I have 3 plus or minus the square root of 2. So I have x equals 3 plus 1 divided by 2 and x equals 3 minus 1 divided by 2. That's what this plus or minus means, right? We're determining if I have 0, 1, or 2 x-intercepts. X equals, if I have 0, I will get a complex number. Just a warning. Okay. So I have x equals 4 divided by 2, which is 2, and x equals 2 divided by 2, which is 2. So my zeros, or my x-intercepts, are when x is 2, y is 0, and when x is, that was supposed to be a 1, or when x is 1, y is 0. Now, in the case of higher degree polynomials, it may be more complicated to determine where the graph intersects the x-axis. This is when you might want to use a graphing tool. I recommend Desmos because it's free and online. In some instances, it is possible to factor the polynomial entirely to find the zeros, and in some cases, it's impossible. So we're going to examine these zeros later on in the text. Algebraic functions are any function constructed from polynomials by adding, subtracting, multiplying, dividing, or taking roots. Okay? So two types of algebraic functions I want us to look at are rational functions. Rational meaning a ratio of two polynomials, and root functions, meaning they have either a square root or a cube root, something like that. A rational function is a quotient or ratio of two polynomials, such that f of x equals p of x divided by q of x. The domain for a rational function is the set of all real numbers for which my denominator doesn't equal 0, because remember, we cannot divide by 0. So I need to define what the domain is of this function. So I'm going to take x squared minus 3x plus 2 equals 0. Well, I need to know how to factor this. So I'm going to go ahead and find the factors of AC that add up to B. I have a video on that under college algebra if you need it. So find the factors of AC that add up to B. This factors to x minus 2 times x minus 1 equals 0. And so I can figure out which of these values by using the zero factor property and setting each of my factors equal to 0. I know that my domain is all real numbers except when x equals 1 or 2. Awesome. We had also factored this on the previous slide. A root function is a power function in the form of f of x equals x to the 1 over n, where n is a positive integer. Okay? When I have a variable raised to a fraction, that means I'm going to be taking a root. So I can take the second root, which is also known as the square root, or the third root, which is the cube root. So these are an example of some root functions. Root function, what it does is it pairs each number with its principal square root. Remember that square root of 4, its principal square root is 2, but it could also be negative 2, because negative 2 squared is 4, right? Square roots undo squares. But we're putting it with its principal or positive square root, okay? The most basic square root function is the square root of x. Its domain goes from 0 to infinity, and its range is the same. And it starts at the origin, which is 0, 0. Here I have a cube root function. It pairs each real number with its cube root. Remember that the cubes of negatives are also negative. So if I took the cube root of a negative, that's going to give me a negative as well. The cube root of negative 27 gives me a negative 3. Etc. So its domain and range are negative infinity to positive infinity. So why don't we go ahead and find the domains of a few algebraic functions. So for this first one, what I want to do is I need to set my denominator equal to 0. I have 3x squared minus 1 equals 0. And I want to go ahead and solve this. So I'm going to go ahead and add 1 to both sides. So I get 3x squared equals 1. I divide both sides by 3. I get x squared equals 1/3. And then square roots undo squares. So I'm going to take the square root of both sides. So I have x equals plus or minus the square root of 1/3. So my domain is going to be all real numbers except where x, as long as x doesn't equal plus or minus the square root of 1/3. Now for this next one, I need to set my denominator equal to 0. So I have 3x squared plus 4 equals 0. If I subtract 4 from both sides, I have 3x squared minus 4. This is number 1, this is number 2. I divide both sides by 3. I get x squared equals negative 4/3. Now here's a problem. I'm going to have to take a square root of a negative. that's going to give me a complex number. So let's go ahead and look at this denominator again. This denominator is a special case. Will this denominator ever be negative? No. If I have x is 0, I get 0 plus 4, that's positive. If I have x is negative 1, that gives me 3 times 1, negative 1 squared, which is 7. Wait, 3 plus 4 is 7. And the same thing is true for positive 1. So the domain of this function is actually going to be all real numbers because my denominator can never be negative. So let's go ahead and make ourselves a little bit of room. It's very cathartic to erase things. And we want to go ahead and find the domain of these these root functions. So if I have 4x minus 3x, this is a square root. I know a square root can never be negative. We are working with the real number line. Real numbers, complex numbers are not for us right now. So I need to know when this is going to be greater than 0. So when is 4 minus 3x greater than or equal to 0? Okay, this is going to be my domain. I'm going to add 3. Actually, I'm going to subtract 4 from both sides. That gives me negative 3x is greater than or equal to negative 4. I go ahead and divide both sides by negative 3. When I divide a rational function by a negative, I have to flip the sign. This is number 3. That gives me x is less than or equal to 4 thirds. So my domain is going to be x as long as x is less than or equal to 4 thirds. All right, let's take a look at problem number 4. Now this is a cube root, 2x minus 1. So cube roots can be negative. If you remember from our graph of a cube root, which I'll go back to, right? The graph of a cube root, its domain is all real numbers. It's not restrained like its friend, the square root, away from having answers that are negative. So this is another special case where our domain goes from negative infinity to, you guessed it, positive infinity.